Maclaurin's theorem. Okay, let f of x be a function of x. Now let's say this function can be expanded in ascending order of x such that the expansion is differentiable term by term, any number of terms. Okay, what does this mean? Let's say f of x is equal to whatever that function is can be expanded into a series. So a1 a0 plus a1 x plus a2 x square plus a3 x cube and so on. Now let's differentiate this. So if we differentiate it, what will happen? We get what? We get a0 will disappear, a1 plus 2a2x plus 3a3x square plus 4a4x cube and so on. Okay, let's differentiate it once more. This will disappear now. So we'll be left with 2 times 1 a2 plus 3 times 2 a3 x plus 4 times 3 a4 x square and so on. Let's differentiate it once more. What will happen? This will disappear. So 3 times 2 times a3 plus 4 times 3 times 2 times a4 x and so on. So if you follow this pattern, nth derivative would be what? So n times, and then it keeps getting reduced, right? So n minus 1 times n minus 2 and so on till when? Till 2. And we can write 1. Yes. an plus say 3. Okay, next what happens? This is 3, this becomes 4. So n plus 1 times n minus 1 and so on up to 2 times 1, and this will be n plus 1 times x plus, next one what will happen? It will start with n plus 2 times n plus 1 times n plus n times n minus 1, and this will keep on going up to 2 times 1 times a of n plus 2 x square, and this will keep on going. Okay, now let's see. Let's say x is equal to, what happens? F of 0 becomes what? a0. F prime of 0 becomes what? Let's, here we put, so this, here when we put x equal to 0, this only a1 is left. So a1. Now f double prime of 0 will be what? So again x, all the other terms except the first term will be 0. That will be 2 times a2. F triple prime of would be what? 3 times 2 times a3. Okay, so let's just evaluate it here itself. F n0, nth derivative of f at 0 is equal to what? See, 3 times 2 times 1, 4 times 3 times 2 times 1. So this is nothing but n factorial and an. Yes, okay. Now let's make it a naught equal to what? F of 0. Here a1 is equal to what? F prime of 0. a2 is what? F double prime of 0 divided by 2. a3 is what? F triple prime of 0 divided by 3 times 2. And in the case of nth term, an is equal to fn0 divided by n factorial. So which means this expansion f of x will become what? F of x is equal to, we started off with a naught plus a1x plus a2x square plus a3x cube and so on. Finally an xn, and this can keep going. Now let's do the substitutions. F of x would become what? A naught is f of 0 plus a1 is what? F prime of 0 x. a2 is f double prime of 0 x square divided by 2 factorial plus, just keep doing the substitution here itself, f triple prime of 0 x cube by 3 factorial and so on, and the nth term would be fn at 0 of x to the power of n by n factorial and so on. Now this expansion is called Maclaurin's theorem. Okay, let's see how this is useful, and it's very useful. But let's very briefly look at how it looks graphically. So let's say I have a graph. Now I want to know at a 0 how the graph looks like. So when I have f of 0 a naught, that is f of 0 is here. So at 0, this is where it is. But if I plot it, I'll get something like this. Okay. Now I differentiate it. So first I took only the first term. Now I am taking the second term. This will give me the slope at this, right? So this will become something like this. Then I find the slope of the first derivative. Again I get this next derivative. So slowly what will happen is this graph will slowly superimpose over the original graph, and especially around the 0 it will map perfectly. How much perfectly? That depends on the number of terms you take it to. So let's see how it gets applied. Y is equal to, let's say we want to know what is the expansion of cos x. Okay, y1 is equal to, so when we differentiate it, we get minus sin x. Now let's keep writing it in terms of cos itself. So this becomes cos, minus into minus, plus cos pi by 2 plus x. Now let's differentiate again. We get minus sin pi by 2 plus x. Again let's write it in terms of cos pi by 2 plus cos x. So which we get 2 pi by 2 plus x. y3, third derivative, we get again minus sin 2 pi by 2 plus x. Again, write it in terms of cos. So 2 pi by 2 plus pi by 2. So 3 pi by 2 plus x. So like this, nth derivative would look like cos n pi by 2 plus x. Now let's put x is equal to 0. So at x equal to 0, y naught is cos 0, which is equal to 1. y1 will be cos pi by 2 plus 0, which is cos pi by 2. Cos pi by 2 is 0. y2 is equal to cos 2 pi by 2, which is equal to pi. Cos pi is minus 1. y3 is cos 3 pi by 2. 3 pi by 2 is again 0. And nth derivative would be cos n pi by 2, and just one more term, cos 4 pi by 2. So 2 pi would be equal to 1. Okay, so which means if you observe this, when n is odd, that is 1, 3, 5. So 1 it is 0, 3 it is 0. So when n is odd, the nth derivative, or let me just put it as yn is equal to 0. Now when n is even, now here the thing is, it is going 1 minus 1, 1 minus 1. So now this we can write it as minus 1 to the power of n by 2. So if you want to verify, you can just check out n by 2. So remember, n is even. So which means we start with 2. 2 by 2 is 1. 4. 4 by 2 is 2. 6. 6 by 2 is 3. 8. 8 by 2 is 4. Now let's write this minus 1 to the power of n by 2. So here what will happen? Minus 1 to the power of 1. So that is minus 1. Here minus 1 to the power of 2. 1. Minus 1 to the power of 3. Minus 1. Minus 1 to the power of 4 is 1. Yes. So here what will happen? This is minus, y2 is minus, y4 is going to be plus. So be careful about this pattern, because you have to figure out this, right? Okay, so what happens to our function? F of x is equal to, remember, Maclaurin's expansion says f of 0 divided by, we can write it as, if you want to remember it like that, this f prime of 0 x by 1 factorial plus f double prime of 0 x square by 2 factorial plus f triple prime of 0 x cube by 3 factorial, and so on. So let's do the substitutions. Yes, f of 0 is what? F of 0 is 1. 0 factorial is 1 plus 0 plus f double prime is x square by 2 factorial, and this becomes minus 1 to the power of 2 by 2. So these two get cancelled. So which means we can make this as minus and we can remove this. Plus, see, whenever it is odd, yn will be 0, plus x to the power of 4 by 4 factorial times minus 1 to the power of 4 by 2. So this is 2 by 2. So minus 1 square is plus 1. So it remains as plus. So we can remove it. And so on. So 1 minus x square by 2 factorial plus x4 by 4 factorial plus. Now you got the pattern. So this next will be minus x to the power of 6 by 6 factorial plus x to the power of 8 factorial minus and so on. And the nth term would be what? Nth term would be minus 1 to the power of n by 2 x to the power of n by n factorial. This is f of x. But more specifically, this is cos of x, right? So wherever you have this, you can use this. Wherever you have cos x, you can substitute it with this expansion. And especially when we look at infinite series, summation up to infinity, whenever we end up with this type of expression, we substitute it with cos x. Just like for this cos x, let's do it for sin x. So let's do the second one. Y is equal to f of x is equal to sin x. So y is equal to sin x. y1 is equal to cos x. We want to write it in terms of sine. So sine pi by 2 plus x. y2 is equal to cos pi by 2 plus x. Again in terms of sine, 2 pi by 2 plus x. y3, third derivative, is again cos 2 pi by 2 plus 3 plus x is equal to sine 3 pi by 2 plus x. And this will go on, and nth term would be, or nth derivative would be cos n pi by 2 plus x. Again in terms of sine, it would be n pi by 2 plus x. Now let's put x equal to 0. So y0 is equal to sine 0, which is equal to 0. y1 is equal to sine pi by 2, which is 1. y2 is sine pi, that is 2 pi by 2 is pi. Again 0. y3, or the third derivative, would be sine 3 pi by 2, which is minus 1. Yes. And if we follow this pattern, nth derivative would be sine of n pi by 2. Okay, so if you go through this list, you will notice that when n is even, yn is equal to 0, y0 is 0, y2 is 0, y4 will be 0. Okay, and when n is odd, yn is equal to minus 1 to the power of n minus 1 by 2. In the previous this one, we looked at, we created a table, right? You can create a table like that to make sure that you are getting this correctly. Okay, now let's bring in the Maclaurin series, Maclaurin theorem. So f of x is equal to f of 0 by 0 factorial plus f prime of 0 times x by 1 factorial plus f double prime of 0 times x square by 2 factorial plus f triple prime of 0 x cube by 3 factorial, and so on. Now if you do the appropriate substitutions, even numbers are 0, so this is 0, 0, 0, and this will be 1 times x, and this will be minus 1x cube by 3 factorial plus and so on. So if you remove all the zeros, you will be left with x minus x cube by 3 factorial. Then you will have plus. If you go to the next term, this would become plus x to the power of 5 by 5 factorial and so on. So x to the power of 5 by 5 factorial. Next term would be x to the power of 7 by 7 factorial and so on. Basically, as you keep practicing, the moment you get the first three terms, you would get the pattern for the rest. Okay, so this is sine x. Now let's look at the sine x in graphical form. So this is sine x. This is x, right? This is your first term of the series. Okay, this is the second term included. So x, this is x minus x cube by 3 factorial. Then you have this blue one is x minus x cube by 3 factorial plus x to the power of 5 by 5 factorial. And finally this gray one is x minus x cube by 3 factorial plus x to the power of 5 by 5 factorial minus x to the power of 7 by 7 factorial plus x to the power of 9 by 9 factorial. So as you notice that this graph, the series graph, as we keep adding terms to the series, it tends to start hugging the sine curve, right? And the more terms you add, the closer it hugs the sine x. So that's the power of Maclaurin theorem, which allows us to generate this series for any given function around x equal to 0. This is very, very powerful. So please practice. Bye for now.